So 3D printing. All of us have heard of it. A lot of it seems like you download some files off the internet, you print what you get. I mean, that's where I got these duck schematics, to be honest. Like you throw it in Cura and you slice it and you print it. And you'll have access to that from the Maker's Studio. But what if you wanted to do more things? Like, for example, Robotics Club logo. I designed those using some software and a picture. We printed them out, handed them out during the last club fair. What if you wanted to do more things? For example, I want to print PCB boards. I have a CNC router here in my room, but I don't have anything to hold the copper clad boards. So I measure them. It actually fits so tightly that I don't even need to have anything else to hold it. Like, this is a copper clad board. It just locks right in there. So when you 3D print something and design it right, they actually do some pretty cool things. I'm making for my senior project this type of thing. It's a battery holder. I've wired it so that essentially when it locks into the mechanism, that it will transfer power from the battery that's going to be contained inside, which is locked in by screws, and transfer power to the drone that we have. I have a whole base station set up for it. In fact, let me show you how I designed that. Let's see. This is going to be share screen. We're going to share screen 1, 2. All right. Can everyone see what I'm sharing? Hello?
Yes, sir.
All right, so if everyone can see, sorry, I'm not used to being on the presenter end very often. I finally got my chat up. All right, so let's just start with things you can do. So for example, I have this entire assembly for something that's going to be printed, mounted on a drone. Here's a clamping system that works together with it. I can even go into the animation studio, and my current animation's broken because I've been redesigning the parts. But when it was working, let's see, public showcase, battery stuff. Okay. I was able to design all these parts and animate it very quickly in Fusion 360 to show what all of these parts did. I was even able to turn it into a GIF for future reference. And I presented this to my SDP, and we got a whole bunch of funding, and we're doing a whole bunch of cool things now. But anyway, that being said, you know, I can make joints, tell it to do all these things, but how, I guess, is the real question. So what I'm here today is to show you how to do all that. I have a new design here, and it's literally just a block. But you know what? The block is boring. This block was dead, yo. Hopefully that's not copyright infringement. So let's just get rid of it and start fresh. So the way this works is you're given this palette, this open palette to design when you have all these things. Now, if you have the free version, you can only have 10 editable documents at once. I'm at 5 right now. And if you want to start following along, this is the time. So we have an untitled blank workspace right now. All I did was go File, New Design. That's all we got. So let me delete all these. All right. So when you have this new design, it's a blank canvas. This is just grid paper, essentially. So let's start drawing. You create a sketch. You place it on a platform. Mind you, the view controls are kind of weird. So let's talk about those for a second. It'll actually be easier if I quickly just draw something. That way you can see what I'm talking about. Solid extrude. Don't worry, I'll go over all this again. So I just made a block real fast. When you want to move around inside the view screen, you can click your middle mouse button to hold and pan around the screen. This will allow you to see things. Part of the hardest part of learning this software is learning how to view all the different designs and stuff. So being able to quickly just grab it, move, pan around your screen is great. Up here in the corner, you have this block, which gives you all your isometric views and your different views. You can rotate around, go upside down. You can look at your product essentially from all angles, which will allow you really to, I don't know, it's kind of hard to design something you can't see, right? And then of course you can go in here and just delete anything you made. So you start off with sketches. You have to pick a face for it. I like starting top-down view. So when you click this box, you can go top. Now you're looking at it. Your axes here are your Y and X axes. Your Z axis you can't see unless you change your viewscape. So this is now the Z and X axis. And you can see from the cube, it's showing you that. Can everyone still see well enough? Awesome. So what you do is, let's just get rid of that. You go here to this solids menu. This is your menu of all your different tools. And you say create a sketch. And I start with this flat face. Now, when you create a sketch, it's just a 2D CAD drawing. That's all it is. All right. It's nothing super fancy. You just draw the shape of what you want. So for example, let's say that I wanted to draw a soccer bot car. So I'll get to this in a second, but some dimensions you might want are 100 and I don't know, 70. Just a bit as a base platform. Oops. And so now you just have this solid rectangle. But what are you supposed to do with it? There are no spots for tires. There's no spot for a breadboard. Where are you going to put your circuitry, your mounting holes? This looks like nothing, right? Well, I mean, you can easily start going in here and just measuring it out. So I don't know how many of you have looked at or seen what a breadboard is. So I'm holding it up to my camera if you're looking at my picture right now. And you can just measure its dimensions. A lot of you will use these for SoccerBot or other projects. The standard dimensions, just using a basic ruler right here, for a breadboard are roughly 5.5 inches by a small one, 5.5 centimeters by 8 centimeters. Sorry, I'm working in metric for most of this because that's what the default program goes to. You can actually tell it inches if you really want to. You can say, 10 inches if you desperately felt like, and it'll do the conversion for you. But naturally it works in millimeters. And what we're going to want to do is we're going to want to design all the places that we would want things. So for example, let's say I want some tires. And I know that tires are going to be, I don't know, let's say, one thing I do want you to note is you always want to leave space when you're about to make cuts and things, because 3D printers can't actually print to whatever the smallest measurement you have. Generally, I say 2 millimeters is a good distance. So let's go with 4 millimeters to be safe. So now we have, you can't see it, but there's a line here and it gives us actual points. So I like to draw by having these lines. So we have the end of it here and the end of it here. I just told it 5 millimeters. And then I'm going to go in here and just cut out a little bit of this shape to leave an indent for a tire. And let's say that the tire has, oh, I don't know. If I have this tire here, it has the circular diameter of 6 centimeters, which is way too big for this drawing, so this will obviously be a one tire car. But the thing is 3D printers can only print so big. You want to keep your prints down to as small as possible. We can probably put like a little front mounted tire on it to balance it out. But you can also trace down from your lines, get this dotted line to tell you when you're even. And then I can just go up and say, all right, I want, we went, if you ever want to inspect something you did, there's an inspect tool here and it tells you the length when you click on it. So that's 4 millimeters. So again, dragging down 4 millimeters. Follow along this trace. And I've made boxes on both sides. And then I go to the trim tool and I remove this extra line. So now I have an outline that doesn't look like much, right? And we can add mounting holes for whatever we want. But I think what you guys want to see is not just this. You also want to see it do something, right? So let's go ahead here and extrude it. Now what extrusion does in basic terms is you take whatever your drawing is, this flat 2D drawing. Excuse me. So you have this flat 2D drawing, but, and you can see that if I do here, it's flat completely. But I want to give it volume. And remember how I said you want things to be small if you're 3D printing them. So let's only give it, another height of, I like the number 4 millimeters for a lot of heights. This might be overkill. You can probably do it with 2, but this gives you a substantial amount of block to work with. So you tell it the height and it literally makes that shape going upwards. Is everyone following along? Are there any questions so far? Am I going too fast or too slow? Is everyone still alive? Okay. So now we've extruded this part. This means we now have a 4 millimeter thick block of thing with 2 cutouts. Well, that's cool and all, but what are we going to do with it? Well, let's say that this is the back of our car if we use our imaginations. And you have 2 wheels in the back and we'll have a front wheel. Let's add a holder essentially for the front wheel, which we can make later. So let me go ahead and make another sketch. So now you see the sketch actually started at the very top of my piece. So if I start drawing here, it's going to actually make the drawing on top of this piece of block. And I can just, this is a little trick I like to do, is I like to make lines to give me my distances. So I'm just going to say that there are 2 lines here. And then at the halfway point of each line, which is designated by a triangle if you hover over it, I'm going to make another little rectangle. Let's see, come on, there it is. And, we don't want to make this too long. This is already, 10 centimeters. And the build plate of even an ender is only 20 centimeters. So let's say we have a build frame of about 8 millimeters. We go look here, there's nothing there. We go back to extrude, we extrude it downwards. until it matches up with this. We want to say the operation is a join, and I'll tell you about these operations in a second, but this will just add it on to our current drawing. So now that we've added on to our current drawing, oops, going the wrong way here. Now we have a front piece. And this front piece, we need to drill holes into, because let's say we're going to have like a little bottom wheel in the front of it. And let's just assume the most standard screw size for small things like this is going to be 3mm. This is just something I know off the top of my head. I don't expect you guys to know that. But let's just say that it has a plate that is, I don't know, 50, no, 6mm by 6mm. And then we need 6. So let's say we have screw holes here. 6mm by 6mm blocks, all right? Or really 6 by 12. So say that we have holes right here for 3. And we have holes right here. And these are going to be screw holes, but we want them on this side too. So let's just mirror them instead of trying to copy them again and again and again. In fact, let me get rid of this line. I don't like it. So what we'll do is we'll say mirror. This will bring up the mirror menu. You select the objects you want to mirror. You select the line you want to mirror across, and luckily we have a midpoint line here. And we've now created 4 holes. Hooray, what are we going to do with them? Well, the Extrude tool is always a fan favorite. And you select all of the areas you want to extrude. Now notice, if I wanted to, I could just extrude a half circle because we have this line going through it. But I want to extrude the full circle this time. You have to select, I could even extrude here if I wanted to. Any face or object I want to, I click on it and it'll allow me to extrude it if it's within the current drawing. And since we're drawing on top of this, any lines or contours on top of this block are going to be part of our general way of, what's the word I'm looking for? Any lines or contours on top of this box are going to be within our purview. But instead of extruding out, because this would just be weird, we got these 4 cylinders coming out of the block. Let's go down. Now, notice it automatically changes the lines to red. This actually means that it's doing the operation of cut. Now, we could just join it again, which would again give us those cylinders, but we do want to cut. This will give us 4 holes for screws. So now we actually have screw holes going all the way through the block. And again, 3M screws are the most common that you'll work with in terms of this kind of electronics. For Arduinos and whatever, they're all pretty much based on M3 screws. Some of it's M2, but that's a little more rare. So now we have a holder up front. Yay! What does this holder do? Well, we don't have a tire. We have to make more components. So for now, let's stick with this. We also want to be able to hold a breadboard. Now, in terms of holding a breadboard, excuse me, as I mentioned before, the measurements were 5.5 centimeters and 8 centimeters. So let's just go ahead, go back into our draw tool. We'll go from this corner over here and we'll say, oh, actually, let's figure out how long this is. It is 70 millimeters. And we want the breadboard to be centered on the back of this because people like nice centered things. Well, the short edge of the breadboard is 5.5 millimeters. So with some basic calculations, or 5 centimeters. So we say 70 minus 55 equals 15, divide by 2 equals. So now the math that I just did will give you how far you need to be away from this corner edge in order to be centered with your breadboard. So let's just go ahead and make that. So 7.5 millimeters. And then we're going to say that it goes out, oh, I don't know. What are we looking at here? 80. And then obviously 55. And then you come back down. And we've made a square. Congratulations. What this square does is it represents the breadboard. And what we can actually do is we can either do one of two things. We can solid extrude, my favorite tool, and just make a platform for the breadboard. We could cut into this to make an area for the breadboard. Or, and this is what I was always going to choose, we could make this just a little bit thicker, just 2 millimeters. And now we have an indent for the breadboard. Most breadboards come with a little sticker on the back you can peel off and just paste it right there into that indent. So now we actually have an indented area for a breadboard, 2 indented areas for tires, and a front area where we could screw on a 3rd tire for stability. It's actually starting to look like something, but it still looks pretty blocky. So let's go ahead and refine this even more. First of all, we're going to need mount points for our wheels, right? And so far, I've only showed you 2D drawings on this bottom face, but we can do so much more than that. All right, so now we're looking at a side view of our original robotic car. And let's say we want to mount this tire in the center. Well, that's easy. We create a sketch right here. If we draw a line across this, we'll always get this midpoint. You see, it's got a little triangle to tell you it's the midpoint of this line. What does that do for us? Well, we now need to create a motor mount. So this, if you guys can see my camera, is probably the most common toy motor used for cars, and it's probably what's going to be included in the object detection kit. It's a 6-volt battery. It's a 6-volt motor with a toy gearbox, and these edges make it really easy to attach basic wheels to them, like this toy wheel that I have right here, which will probably also be in the kit I mentioned before. And let's design a box that we could put this into. So now that we know that this is the center point, let's measure this motor. This motor is, let's see. Let's say it's 2.5 centimeters wide. It's really more like 2.3, but. So that gives us a length of something along the lines of this. We actually don't want to get in the way of our breadboard area. So let's mount these motors underneath the block. And since we're mounting them underneath the block and it's 2.3, so 23, 23 divided by 2 equals 11.5. So we want lines that are, 11.5 this way and 11.5 this way. And then we make a solid block here. Let's see. That was, if I stuck it like this, I think I actually measured this wrong. No, I measured it right. And then it is Is this a perfect square? No, I measured it wrong. It is 1.8 across, 1.8 centimeters. So these actually need to be, and this is good. You can see that all I have to do is double click the number, change it. It changes the length. Then all we have to do here is we have to go, what did I say before? 2.7. 2.3. So 23 down. Cross it like this. Follow the dotted line, get it to a 90-degree angle or 180-degree angle, whatever it's saying. And we have a nice little square that our motor now fits into. But what's the biggest problem? Well, this square doesn't account for walls or anything. It's literally just as tight as the motor is. So remember what I was saying about 2 millimeters being my magic touch point here? So we have 2 in the X, 2 in the Y, or 2 in the X, 2 in the Z, whatever. And we make just a tiny box around it. And I'm gonna need to make another line over here, 2 millimeters. And I can just go point to point. We have a box. And we actually want to be able to fit 2 motors, don't we? So let's actually go ahead and extrude this box. Let's see, which way are we facing? All the way through. But wait, I'm extruding the wrong thing. You're right. Let me go ahead and click this and this. Second verse, same as the first. Now we have an area, at least, for our motors to sit inside of. And join and done. Now, let me tell you, this is not super practical to print. Here's why. When you print this, it's going to have to generate supports for this entire area because gravity works. And this is something that a lot of people, when they first start 3D printing, don't understand is gravity is super important when it comes to 3D printing. If you don't have a structure supported and you try and print it, it won't print. It'll just fall straight through. There are a couple of ways to get around this issue. One, round cavities, for example, don't need supports. They just don't. You can print them completely without supports and you are just fine. Or two, you just don't print the cavity at all, which is what we're going to go with here to save materials. So again, I don't want this bottom structure here anymore. So I could draw a square, extrude, cut it off, or what I could do is I could cut on the sides right here and just go from endpoint to endpoint, solid, extrude, click this edge, cut all the way through it. You always want to cut a little bit farther because you don't want to leave like some super thin piece right there. And boom. Now we have 2 brackets. And obviously we'd have to drill out the holes, of course, for the mounting plates for the motors. So again, what you could do is you could go in here, measure that it has 2 holes. About, I don't know, 3.5 centimeters in. Yeah. So what's that look like? And this happens a lot when you're designing is that you end up not getting your measurements right the first time and you have to go guess, check, what have you. And no one has noticed yet, including myself, that I'm designing this box in the wrong orientation. which is easy to fix. I'll just cut it off. Yeah. Basically, I held this motor up before and I was designing it as if you would slip it into that cavity. Problem is these gears are on the side. You actually have to put the motor sideways like this. So, you know, it's a real simple fix that I can just do real fast. I go down here. I say that we're going to go at, what was our width again? Our width was, 1.8. All right, so we'll say it goes in by 19. And then we'll just send it all the way through because that'll be easy. Oops, messed that up. And you can just delete lines by clicking them, selecting them, and hitting delete. And by the way, here's a tool that I haven't shown. You can say sketch dimension, and it'll put the constraints for that dimension right there. So if I change it, like I say 18, if I say 15, if I go back to 19, it'll immediately change it so that it's in the right place. And what I'll do from here is I'll do the same on the other side. I'll say 19, same distance. I'm actually going to make this a center mount thing, center mount set of holes. You can use essentially one set of screws in order to go all the way through. Oh, that's wonky. It actually built it up top, but that's easy enough. We just, yeah, 25 is way too thick. Go away. This is a sketch and it thinks it's locked, but we could just hide it and it'll never appear again, which is the cool part. So now we have this big ugly block. We say that there are holes for this motor. Let's see, starting from the center point where it needs to be mounted. In fact, let's just go ahead and draw the center because that's where it needs to be mounted. You find the center of the block actually by just putting these crisscross patterns. You can extrude a hole, and we want this hole for this spoke to go all the way through it. So we can just say that it's 5. Yeah, so the diameter of the hole is 5. We could easily make it 6 for good measure, not 56. Heavens no. 7 for good measure. And then use the trim tool to get rid of all excess lines. That way they're not in our way when we go and we say solid, extrude, look through it. Done. Now, the reason I want to show this to you is because remember how I was saying a big center cavity, this square cavity in the center was bad before? Well, now it's okay. A circular cavity can be 3D printed without problem, assuming it's not like a big radius. So you can print circular cavities through things without having issues of the extruder just making spaghetti mess everywhere. And obviously we need to do more things to get rid of like this giant blocky statement right here. But let's go ahead and mount these motors. We're going to have it so that they hang out the back. A big radius. 1 second. I would say a big radius would be something along the lines of probably close to a centimeter. Once you get to around a centimeter, you might want to start thinking of supports. Because what happens is, and I'll show you over here on another project I did. So when you get to over here and you're printing these big arches, for the most part, they can be printed without supports. But when it gets to the top, your cutting program might specify this as a straight area instead of rounded, depending on your level of refinement. And because of that, this might not be able to jump the gap when it's printing and will just fall straight through, especially for big, heavy circular arches like this one. So instead, you would want to go into Kira, which, by the way, I'll show you real quick towards the end here. And when you map it out, you would want to print just enough support arches. You can generate supports for your prints so that it'll print upwards this little beam that'll support that last little gap. But for the most part, circular arches don't need supports. I do it just to be safe, because you'd hate to get through a 14-hour print just for it to fail right here at the end. That would suck. I'm actually printing this right at the moment. And I'll show you this in a few minutes here. Sorry, my headset keeps turning off because it's so quiet. It's powered by sound or whatever. Not powered by sound, but like if it doesn't sense enough sound within a certain time limit, it turns off. So anyway, we have this circular radius here. From that circular radius, we know we have 2 holes at the edges, which are at, something along the lines of 2.6 away. Centimeters. Yeah, 2.4. Oops, not what I wanted. You can always Control Z is your friend. And we can say that from the radius here, we want 2.6 or 26, 24. I'm good with numbers. And the holes, equidistant from each other, are at also 2.4. It looks like from edge to edge, not radius to radius. Radius to radius, it's closer to 1.8. So let's say it's 0.8. So, oops, 9, and then 9 in this direction. And then we make 2 holes, again, 3 millimeter. 3 millimeter is your friend for screw holes. And we can go solid, extrude. We can click these 2 holes. We can just cut all the way through it. Boom. This is now a mounting block for 2 motors, because what you can have is you can have 1 motor on one side and 1 motor on the other. And if you really wanted to have 2 separate mounting blocks, what you could do easily is you could say, all right, well, I don't want this giant block of material here. It's 24 in length. So let's go 4 and another 4. And we'll just build a rectangle off of that. And we'll go solid, extrude, as we always do, all the way through. Cut. Now, you have supports on either side that you can screw in your motors to. Now, I don't really like this in particular, because these thin supports will probably break. And that's just how it works, is like they'll break off because PLA is brittle. It's not like some immovable object once you print it. So what you can do again is if you want to try and be a little bit efficient with your material, you can go ahead and just print like some squares here. You can just say, all right, down to the bottom, 25 by 4, and then another 4, and then tab 25. And if you saw how I did that, I'm doing the distances because it automatically gives you one distance. You can type in a number and then you hit tab, it'll let you type in the next number. And then of course, solid extrude those two lengths, bottom. We want it to join, done. So now you have this square. And what do you do from here? Well, let's make one more finishing touch to this plate before we end. The other thing that you can print without having to build supports is angles. So you can always go to modify chamfer and we can pick all 3 of these sides. And we can say, I want you to go in by 1 millimeter. No, that's not enough, 2 millimeters. And now we have a 45-degree angle on this ledge, which should, in theory, be able to print without a problem. You might have to play with those angles a little bit more, but now we have a printable car body, essentially, a very tiny printable car body. And what we can do with this, and I'm going to begin wrapping up my little tutorial here and then let you ask questions, is SolidWorks makes this, or not SolidWorks, I did SolidWorks before. Fusion 360 makes this really easy. You can go to Tools, Make, 3D Print, select the body you want to print. You don't want to send it to the 3D print utility yet. You just want to have it all set up so that it's in millimeters. It goes into STL. You select your body. You say OK. You can name it whatever you want. Super fast car body. Puns intended. You can go into Cura, and I don't want any of this. Go away. Shoot. And we can just go to that STL, and it pops into Cura. But we don't want to print it like this. No. So we have a couple of tools here in Cura. One is the rotate tool. We can rotate it upside down so the flat part is mostly against the bed. This will give us more bed plate adhesion, and it'll also let us print this little indent area without supports, because a 45 shouldn't need supports. Sometimes it might. In fact, it probably will now that I'm thinking about it, because this is such a large body, and that was me being silly. But point is, whatever. It's still better than printing supports for the other side. Yeah, I didn't think about that. Oh well. Anyway, we will have to print supports, so this will be a good way to show you guys how that works. Yay! So the controls are kind of the same. You right click in order to, I don't know, orbit, and then you hold your middle mouse button to pan. You can select your print settings, your filament, and they'll tell you how to set it up for your specific printer when you go to the iLab. But here's a couple of settings you're going to want to know if you're using Cura. 1, your wall count, your wall line count is important, because more wall lines is stronger than adding infill. Infill is how much center stuff, because it prints it hollow. And then it adds so much infill, which is the amount on the inside that it prints. You want this number to be low. That way it's light and doesn't eat up a lot of filament. And you want to increase your wall line count, because the wall lines are actually where you're going to get most of your strength from for a print. This is just how you waste a bunch of filament. And then you can pick different infill patterns, and these different infill patterns have different strength lines, depending on how you print it. depending on what you're printing. I like trihexagon, but that's just me. Printing temperature is all about what material you're printing it with. If you're having trouble printing your first layer, lower your speed for the initial layer. That'll help you print a little bit cleaner on that first layer. Blah, 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 blah. Yes, those are technical terms. Generate support right here. You're going to want this checked specifically for this body because, haha, yes, I definitely intended to print an area that needs supports. That was always my intention. You have to set it to the advanced options in order to get that. So you can look at it from here to see what options you can do, and you have to go to advanced or expert in order to get the first layer speed, but it's super true. It's super useful. So when you generate supports, what it's going to do is it's going to look for this angle that you specify right here. So for us, we know we have a 45-degree angle we don't want to print on. So I'm going to say anything above 60 degrees, generate me some supports. All right. And this is your patterns for it. Slice. And we can preview it. So what it did was it went through and it calculated everything that it would need to do in order to print this. I said that these holes didn't need supports, but because I set such a low number here, it printed them for it. So we'd actually need to go to something like 75 as your overhang angle in order to get rid of those supports in those holes. And like I said, the bigger holes will have larger overhangs. 75 is the most I would go with this to be safe. And then it prints all of this excess material down below in order to make sure that your platform is supported correctly. And it also prints it with these little ridges so that you can easily break it off at the end. So that you can just rip all this off. And then your ugly side, which is going to have any dents left by the supports, are going to be underneath your breadboard anyway, so you won't see them. So yeah, totally intentional. But that's the basics of 3D printing, or 3D design and then 3D printing. I know this was a quick run through. I'll do more targeted workshops later on how to refine it, like adding chamfers and assemblies and making like large, cool things like this, and then maybe animations later. But for now, I think that's a good setup. Oops. Are there any questions? I know that was kind of quick, but maybe a little dry even. Anyone? Now's the time to ask if you got lost. Is there anything you want to see before we end here? Awesome. Well, if all of you, yeah, I know I was going quick and you might not have had the ability to follow along, but if you play with it yourself and you have questions, I'm here to help. I'll be doing more tutorials on how to do more advanced things like revolutions and different types of hole cuts, maybe even work with meshes or scripts or assemblies. There's all sorts of tools you can play with and mess with and do all sorts of neat things. So just make it your own. Have fun with it. It's a very useful ability, even if you're not 3D printing, to be able to make other things. So I hope you enjoyed what I had to show you. And that's pretty much it. Hope the rest of you have a great day.